Welcome to another video in the SimSmith Basics series. This is Larry Benko, and today's topic will be on return loss, reflection coefficient, a little bit of review in SimSmith, and why return loss is something that's kind of important to be able to measure. Let's start off with a pretty simple circuit here. The circuit I've got here is nothing more than a 50 ohm resistor and a 73.5 picofarad capacitor. This capacitor was calculated to give me approximately a 2-to-1 SWR at 50 megahertz, or sorry, a 2-to-1 SWR at 30 megahertz and a 3-to-1 SWR at 50 megahertz. And to make sure that the capacitor doesn't enter into any of the calculations, I've given it an artificially high Q of 10 million. SimSmith, if you do nothing in this field, such as delete it, gives an arbitrary 1 million Q for reactive components. If you put a 0 in here, it also gives you a Q of 1 million, or you can specify the Q. This is a Q of 10 million. Any of those would be virtually a perfect capacitor, so it really doesn't matter what you do. But if you leave the default value, which is defined in the preferences, the default capacitor Q is 2000, which is a good capacitor to use for real circuits. For a lot of times when you want to do something where you want to show a point, you want an ideal component. This component is very close to ideal. The second thing is, I have two numbers in this field. That's a relatively recent addition to SimSmith, I don't know, probably in the last maybe 6 or 8 months, where multiple numbers can be put in the frequency field here. That's really nice. What that does is it puts multiple dots on the Smith chart, puts multiple dots in the square chart too. I don't have anything plotted here, but multiple dots in the square chart. The frequencies here do not need to be ordered. They can be in any random order you want. SimSmith does nothing to tell you what the frequency is here unless you put a marker on top of it. But it does give you the ability to have more than one point. And more than one point that's outlined is really nice. Now, I can put 10 different values in here, and this is a feature that's available right now in this beta version, but it will be in the next real version also. It's a little tricky to edit sometimes in here if I add too many fields like 1, 2 megahertz, 3, 4, 5, 6, 7. I start getting smaller and smaller and smaller. I can go up here and edit the values up here, which is kind of a nice feature. But that doesn't really change the functionality of what we have at all. We have two frequencies defined here. The second frequency is actually the primary frequency. Or let me just say this, the last frequency is the primary frequency. So that if I put a piece of transmission line in my circuit, notice the frequency here is 50 megahertz for the transmission line in terms of the length of the transmission line. If I put an automatic L network in here, it's calculated at 50 megahertz. I can change this, but the default is the second frequency. Likewise, if I put an inductor in here, it comes in at a reactance of plus J50 at 50 megahertz, because 50 is the last value here. So these two frequencies are not equivalent, but they're in terms of adding new components, but they're equivalent in terms of showing points on the graph here. So without any more about that, let's go look at the square chart. So we see exactly what we said. So at 50 megahertz here, we see 3-to-1 SWR. At 30.6 megahertz roughly, we see a 2-to-1 SWR. The other thing SimSmith can plot for us is power. Now, our generator is set to be a UZ0 type generator. That means we have a voltage generator in series with a resistance, which is 50 ohms, which is calculated such that when there's a 50 ohm load, we will get 1 watt out. Now, this circuit is designed here in such a manner that at 1 megahertz, the capacitor is pretty well out of the circuit, and we can see that we get 100% of the power out basically, and the SWR is virtually 1.0 to 1. I think it's actually 1.002 or something. But anyways, it's very, 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 very good. So that's why this circuit was designed this way, to show us a really good match, a 2-to-1 SWR and a 3-to-1 SWR. So SWR we've talked about. I did a previous video, I think it was video 5 in the basic series on transmission lines and SWR and stuff like that. A lot of industry does not use SWR. They use a term called return loss. Return loss is kind of analogous to the rest of the world using the Celsius temperature scale, and we use Fahrenheit temperature scale. And the scientists, of course, use Kelvin. Or it's kind of analogous to describing loss in a reactive component, where some people refer to the ability of a reactive component to be good as loss tangent. They talk about things like dissipation factor. They talk about things like reactive versus non-reactive power in a capacitor or an inductor. Those are all measures of exactly the same thing. Well, in the case of transmission lines, SWR, return loss, reflection coefficient, all are talking about the same things. They're all the children, basically, of gamma. Gamma rules the world, and gamma is basically what SimSmith plots. The Smith chart is a plot of gamma. Gamma is a complex number. I click somewhere here. Gamma is 0.904 at 40 degrees. Here, gamma will be basically 1 at 0 degrees, or pretty darn close. Here, gamma will be basically 1 at minus 90 degrees. Since this is a 2-to-1 circle, here gamma will be basically 0.333 at 90 degrees, 0.334. So gamma rules the world here. However, we don't need to know the actual phase of gamma to determine things like SWR. So SWR is basically determined from something called reflection coefficient. And to put this in a little bit better perspective here, a number of years ago I did a talk on transmission lines, and gamma is this symbol right here. Gamma is defined as basically that, which is the load impedance and the source impedance, etc. But the term rho, which is a Greek small letter p, I guess, rho is the magnitude of gamma, and rho is what we call reflection coefficient. So reflection coefficient is something that SimSmith does not natively plot, but that doesn't mean that we can't get SimSmith to give us reflection coefficient. It's quite easy to do. Also, return loss is defined as this. So if we think about SWR on a transmission line as being a ratio between the maximum voltage and the minimum voltage we see along the line, we can look at return loss, and what we see return loss as being is the ratio of the power that's going forward in the line versus the power that's coming back, expressed in dB. The minus here means that since it's return loss, it's always a positive number. So that means if I was to put a watt into a circuit, I get 1 watt back, a tenth of a watt back, then I would have a return loss of 10 dB, because a tenth of a watt is 10 dB below 1 watt. Let me say it again. A tenth of a watt is 10 dB below 1 watt. Anyways, so why do we need return loss? Well, we'll get to that later, but let's see if we can coax reflection coefficient and return loss out of SimSmith. I did this in advance, but the plot menu, as I've mentioned before, has the power to do this type of stuff. So what we're going to do here is we're going to plot. I'm going to make this a little bit smaller here so we see the stuff that's happening. We're going to plot, and by the way, these two lines do absolutely nothing with the two slashes in front. The two slashes are a symbol to SimSmith that this line is a comment. So we will take those two lines out of it. We'll take those two slashes out of there, and we'll see the plot command. Plot command, and we're going to define the plot command to have a name. That name is this box right here that now just appeared. It appeared when I got rid of the two slashes. So we have a function now called reflection coefficient, and it is nothing more than the magnitude of gamma. Well, SimSmith does not have a reflection coefficient function built into it. It does have a magnitude function built into it. So we just calculate the magnitude of gamma. And where are we going to calculate that? Well, we'll calculate that at right here, at G. Now, what are we going to title the axes? Remember that SimSmith has 4 axes on the square chart that it can plot. The first axis is an axis called power, PWR. That's this one right here. It pops up, it displays watts or dB relative to watts. It has another one called SWR right here. SWR is defined as a solid line. Watts is defined as the dashed line. It can have two more. So if we click down here on reflection coefficient, we see, whoops. We click on reflection coefficient down here. I have to close the window to get it to take. We see another line. And let's go back here again and look at this for a moment. I define this to be, so name of reflection coefficient. Here's the work we're actually going to do, the magnitude of gamma. We're going to title the axes something. You don't have to put anything in here. If you don't put anything in here, we would have had a Y2 up here. But I put rho in there because rho is what's usually used for reflection coefficient. And I'm plotting it on axis Y2. Axis Y1 is on this side. Axis Y2 is on this side. Likewise, we will now also plot something called return loss. Return loss, by our formula, is minus 20 times log to the base 10, and log to the base 10 is the SimSmith function of the magnitude of gamma. And we're going to give it a heading of return loss in dB, and it's on axis Y1. So if I take both of these, I close them off, and I click on return loss, I now have 4 graphs. Well, these two blue graphs are kind of annoying in that they're the same color, so let's go in here and use SimSmith to let us pick a different color for that graph. Now we have 4 different colors. We've got a blue graph, which is SWR, down here. We've got a pink graph, which is power. We have a red graph, which is reflection coefficient. And we have an orange graph, which is return loss, and return loss is in dB. Reflection coefficient is unitless. It's just a number. And all three of these things, not the power, but reflection coefficient, return loss, reflection coefficient, and SWR all describe the same phenomena. If you know one, you know all 3 of them. So let's look at these carefully here. So at 30 megahertz, let's go to 50 megahertz first. At 50 megahertz here, the SWR is 3 to 1. We know that at 3 to 1 SWR, when the wave gets to the end of the load, what we reflect is half. So the reflection coefficient is basically 0.5. A 0.5 reflection coefficient coming back means that the power that you get back at the load is basically 1/4, assuming there's no loss in the circuit. So you would be down by a quarter of the power. So the power being 1/4 is 6 dB down. So now let's look at what the return loss is. So we click on return loss, we see it's 6 dB. And 1/4 of the power is exactly 6.02 dB. Likewise, in the case of the 2 to 1 SWR, a 2 to 1 SWR right there, 1.997, manifests itself as a reflection coefficient of 0.333. Didn't quite click on it exactly. And 0.333 is 1/3 of the voltage coming back. 1/3 of the voltage coming back is 1/9 of the power. 20 times the log of 1/9 is minus 20 times the log of 1/9 is 9.55 dB. All these say the same thing. And it's probably getting a little monotonous to hear me say they're all the same thing, but I'll move off of this here in just a second. The other thing that's down here is a thing called mismatch loss. We've talked about mismatch loss before. That's an opportunity that the generator had to produce 1 watt into this circuit. But since we faced this circuit with an impedance that was not appropriate for the maximum power transfer from the generator produced less power. Mismatch loss, again, is tied to rho. Very interesting. Minus 10 log the base 10 of 1 minus rho squared. We could plot that just the same way we plotted the other two. But we see it here directly in the power that is actually delivered from the generator. And to be more correct, this shouldn't be this. We should be looking at the power delivered into C1. But since C1 is a lossless component, both the two curves are exactly on top of each other right here. So it really didn't matter which one we did. But we noticed that this generator produces 0.889 watts. Well, I just said a minute ago with a reflection coefficient of 1/3 coming back, reflection coefficient 1/3 right there coming back. That's 1/9 the power. 1/9 the power, so we have 1 watt minus 1/9 of a watt. And what do we get? 8/9 of a watt, 0.889. Pretty cool. And in the case of 3-to-1 SWR here, the 3-to-1 SWR has a reflection coefficient of 0.5. That means 1/4 of the power comes back. And what do we see here when we look at this? We see 3/4 of the power going out. So our power here is reduced by 3/4. So we have 1/4. Let's say it again. We have 1/4 of the power coming back. That 1/4 of the power coming back is due to the reflection, but the mismatch loss due to the impedance we see only lets us produce 3/4 of the power. So if we want to produce all the power, what we have to do, and this is a function built into SimSmith, is create a generator that has is of type X match. An X match generator basically says, and when I click on this, you'll notice that this resistor goes away. When I click on this, we get a matching network here. It's a perfect mathematical matching network. It allows the generator now to produce 1 watt into the circuit no matter what the impedance is. It's the tuner you would like to be able to have built into your radio because it's perfect. And we see up here that we get 1 watt. At any SWR, it doesn't matter where we are, we get 1 watt delivered into the circuit. That did not change any of these values though. The amount we reflect percentage-wise is still the same. So reflection coefficient tells us the percentage of reflection in voltage or current. Return loss tells us the percentage of power that is reflected in dB. And SWR tells us the ratio of the maximum to minimum voltage or current, all describing exactly the same thing. So now let's talk about why return loss is actually a parameter we might want to have. One little aside here before we get started. This is another graph here that just basically shows all these items graphed with a various sort of SWRs. At low SWR, the reflection coefficient is low, the return loss is high. That means 26 dB less signal is returned than what was put out. Mismatch loss is very low. We get a lot of power to the load directly. And here's the percentage of power delivered to the load. And this table is nothing more than what you would take off of this graph, but it's easy to come across. And it explains things pretty easily. Another thing is there's actually a bunch of little calculators you can find on the web that describe this all. All this is described in these calculators. Here's a case where we have a 2-to-1 SWR, which shows the standing wave ratio to be 8.7 to 1. Let me get rid of this one here for a minute. So we go to 2-to-1 SWR here. I'm sorry, 2 dB return loss. Let's set the return loss to be, well, since I did this with SWR, let's start with SWR. A 2-to-1 SWR has a 0.333 reflection coefficient, which we saw before, and had a return loss of 9.54 dB. To get it, didn't quite click on that exactly. A 3-to-1 SWR has a 0.5 reflection. 3-to-1 SWR has a 0.5 reflection coefficient and a return loss of 6.02 dB. This calculator is old. I mean, it is so old. It's 2000, but it still runs, and it's cute, and it kind of keeps this all this stuff in perspective. So now with both of these gone here, let's change the circuit a little bit here. We're going to take the capacitor out of the circuit, hit the control key and hit the component, it goes away. And we're going to replace that component with an attenuator. This is just an in-network I built that's an attenuator. The function here is, if you want to see what the function is, just stop the video. But basically these formulas are available on places like, I think EEWeb, Microwaves 101, a bunch of other places. They're available in the textbooks and stuff, but they describe the components in a T attenuator. And I just plotted them. There's the circuit I built as an in block. It could have been built as a ruse block. It could have been built lots of ways. This attenuator is 1 dB attenuator. And this 1 dB attenuator, just for clarity, is exactly the same as this circuit right here, where this component is 2.87 ohms. This one's 2.87 ohms. And this one here is 433 ohms. This circuit is exactly what this does. That's all. This just happens to be in one block, so it's kind of convenient. Plus, I can just change the attenuation. So we didn't really do anything different than what we had before. We're still looking at everything we had before. We've got a 1 dB attenuator in here. Let me change that attenuator to be 3 dB. So now let's look at what we actually have now in this circuit. And let me go back here and let's put the load impedance and make it, well, let's leave the load impedance 50 just to start here. At 50 ohms, what do we see? Well, we see our SWR. Let me get rid of all this stuff here. We plot our SWR, and what do we see our SWR as? 1 to 1. It was down at the bottom here. It was hard to see. Why is it 1 to 1? Well, this is a 50 ohm attenuator into a 50 ohm load. The impedance here is 50 ohms. SWR is perfect. And if we plot our power that goes out of our circuit, right here we see it's 1 watt. We see it's a half a watt into the load because it's a 3 dB attenuator. That's again all very consistent. And if we basically look at the reflection coefficient here, what do we see for reflection coefficient? 0. And you'd expect the reflection coefficient to be 0 because it's a perfect load again. Likewise, if we look at return loss, we expect to see the return loss. It's going to be really, really high, 300 dB. That's an internal limit probably in the accuracy of SimSmith. So let's take this circuit, though, and replace it with a 0 ohm load. A 0 ohm load has 100% reflection. Now, what do we see with a 3 dB attenuator in our circuit? Well, let's see if we can get these graphs all to be on screen again. The SWR is 3 to 1, looks like. The reflection coefficient is 0.5. The return loss is 6 dB, and all these are constant flat with frequency because this circuit has no frequency component in it. The load power is obviously 0. The power delivered into the circuit, though, is 1 watt. So this is interesting. Notice how we have a return loss here of 6 dB. We have an attenuator of 3 dB. Our 3 dB attenuator took our power that came into the circuit, which was 1 watt, halved it, 100% of that was reflected, halved it again, and what do we get back? 1/4 the power, 6 dB. So a lot of components like attenuators, and for that matter, even industrial antennas are specified in return loss. You'll see an antenna that has a return loss characteristic versus frequency. That can be converted to an SWR plot, although not generally in your head. You can convert it. But if I was to go buy an attenuator, and I thought maybe I damaged the attenuator somehow, one of the resistors in the attenuator here has been compromised. How could I determine that? So for that to be the case, let me go back here and change my 3 dB attenuator here to be let me make it a passive, an individual component attenuator just real quickly here. So this was 8.55 ohms. 8.55 ohms, and the shunt was 141.9 ohms. That's close enough. And we'll get rid of this component. We expect to see a 6 dB return loss. If this component had been heated up, let's just say, and became 10 ohms, let's see what happens here. Before we do that, let's look at this circuit again with an open on the output of it too. Make it 1,000,000 ohms. Watch the graph here when I hit enter. Hardly anything changed. It moved a little teeny bit there because a million wasn't enough. It could have made it 10 million or something. But basically, it's the same graph. So now let's change our resistor here to be 10 ohms. We're trying to check and see if our attenuator is good. We see a change. Let's put our put a 0 ohm load there, and it's different too. We can see basically that the return loss is no longer appropriate. And we're using return loss primarily here because we know what the expected value should be for any type of an impedance. So if I turn off SWR, turn off reflection coefficient, just look at return loss, we see the return loss here is somewhere now around 6.7 dB. Again, it should have been 6 dB. And if it had been, this resistor had been 10 ohms instead, we'd see it also. We see it differently. When this is a high impedance, we might not see it here. We don't see it here. But that's why we need to look at the attenuator with both short and open here, and then flipping the attenuator around both directions. If we do that, we can find if there's anything wrong with the attenuator. We're doing that basically with a antenna analyzer. The device we're using to make the measurement is a single port device. We don't need to have a two-port network analyzer to see if our attenuator is good. A single device like an AIM 4170, 4300 has a single connector on it, can read this impedance, measure return loss, and give us the answer. Of course, a two-port network analyzer that has a generator here and a receiver over here can measure it directly. But the cost of the single-port analyzers is really inexpensive these days, and the cost of the two-port analyzers is still a little bit pricier. So I suspect a lot of people will have a single-port analyzer versus a two-port analyzer. So let's continue this discussion a little bit further here. What happens if we put a piece of transmission line in here? Can we use this same circuit to determine the loss of our transmission line? And the answer to that question is yes. Let me get things straightened back out again here now. We have not a very lossy piece of transmission line here. It's not very long. Let's make it a little bit longer. Let's make it, say, 10 feet long. And our return loss now is going to be pretty poor because we put our signal out here, we get most of it back. Now we're doing it with an X-match load. It really a generator. It doesn't matter if it's X-match or if it's UZ0, because the fact that we get less power into here, our analyzer measures the relative difference between the power output and the power input. So it doesn't matter which type we use. And if we change this back to X-match again, you see that the curve didn't change. And that was exactly what we would expect. It doesn't change. However, I see this really funky curve here. What do I make of that curve? Well, I would expect that as frequency would go up, you would see the loss in coax increasing. Yet it doesn't appear to be the case. We see the loss increasing here, and then all of a sudden we get to a certain frequency and we see the loss in the coax actually decrease a little bit, then go up, decrease a little bit, then go up. What if we change the length of our coax to something different? Still the same thing. I don't know where I was before. Let's leave it at, say, 20. There's a 20-foot piece of coax. What is the loss in this coax? Well, it's hard to read from here what the loss would be. What happens if we put a 0 ohm load out here? Oh my gosh, it just changed. That's unfortunate. Now which one do we use? Let's put them both up here on the scale at the same time. I'll put a isolation block in here. We'll make the second isolation block be open. The first isolation block is short. We'll take this, we'll copy it, Control-C, Control-V, we'll put it back over here. And now we've plotted the return loss here. We need to plot the return loss here. So let's go back here, plot an additional return loss. We'll take this one here, we'll copy it to there. We'll call this return loss 1, say. Actually, we'll call this return loss short. We'll call this one return loss open, which is what it is. But this one is not looking for the magnitude at G anymore. It's looking for the gamma at T1. Hope everyone's following what I'm doing here. And now we have two of them we can turn on. Oh. Need to turn the clone load off. I typed the value in, but I forgot that this was cloned. So now let's put our open in here. Now we have two curves. If you've got a little antenna analyzer, the first time you see this, you probably think there's something wrong with your antenna analyzer, but this is exactly the way it works. And it works this way for a very simple reason, and that is because over the piece of transmission line, the high loss and the low loss sections, and I described this in the video on transmission lines earlier, the loss is not linear per unit length. And based on the frequency you've got, and based on the kind of length you have versus the frequency, you end up with a different number of lower loss sections and a different number of higher loss sections. And those lower loss and higher loss sections contribute in such a way that as you change the frequency, the loss actually can go down a little bit, which is really, really interesting. And it was something I was really surprised. When I saw this probably, I don't know, I think the first time I saw it was probably about 20 years ago, I was absolutely amazed. But I started this with asking the question, could I measure the loss of the transmission line? And the answer is yes, we could. The loss is probably a line that runs down the center here. It's pretty hard to draw a line through the center of this, but if we're out here a ways, let's see what happens. Let's define our coax to be something that, so we don't have to do a lot of work here figuring this out. Let's just say the loss of our coax is going to be defined to be 1 dB per 100 feet at 50 megahertz. And this doesn't change the analogy here at all. All it does is give me a place at 50 megahertz where I know what the loss should be. It should be 1 dB at 1 dB if it's a 100-foot piece of transmission line at 50 megahertz. Well, we've got a 20-foot piece of transmission line, so that's 20%, or it's 0.2 of 1 dB. So it should be 0.2 dB. Well, 0.2 dB going down, 0.2 dB coming back up, 0.4 dB. 50 megahertz here, where are we? This value sits at little bit over 0.4 dB, 0.4, say 0.407 dB. This point sits at 0.391. We average 0.407 and 0.391. We get like 0.398 or 0.399. That's pretty darn close to 0.4 dB, which is what the expected value is. So your little antenna analyzer can be used to actually measure the loss in a piece of coax if you wish. Again, like I said before, if we were down here at this frequency and trying to make the measurement, or if we were to shorten the length of the coax to be like 5 feet, say, it's a little harder to measure the loss is less. The loss would now be 1/20th of a dB times time out and 1/20th of dB back, which would be 1/10 of a dB. And we can see it's roughly a tenth here, but our two numbers that we're averaging are a little bit further on either side. Again, the number's probably not too bad here. So 0.12 averages with 0.8. You can see where 0.1 is. 0.1's right there. It's pretty close to the center of that. So again, you can use it. Like I said, down here is probably a little bit trickier. But this is an interesting experiment to do. And this is primarily why I use return loss a lot of times on my network analyzers. My network analyzers will read SWR, but for a case like this, return loss is actually a more useful function. And again, SimSmith doesn't include it natively, but it really doesn't take very much effort to actually just make SimSmith give us the answer we want. If SimSmith provided all these functions, and Ward may see this and add the next version of SimSmith a return loss function, who knows? But nevertheless, you can always produce it this way. It's pretty easy to do. It has a usefulness, and this explains exactly what I saw 20 years or so ago when I first saw this, and I thought there was something wrong with my calibration of my network analyzer, and I thought there was something wrong with my test fixture. I thought there was something wrong. But indeed, this is exactly how transmission lines work. So anyways, hope people thought this thought this was useful and found it interesting. I'm planning on one more video probably with a bunch of little anecdotal things that SimSmith can help us do. And then after that, I think I'm going to stop with the basic series of videos, unless there's some new features that come out in SimSmith that would fit to go, fit back in the basic series. I've covered what I think to be most of the ideas that I would consider to be basic in SimSmith. And if anyone has any suggestions, I'd be willing to hear them and see if I could produce something that would address those issues. But otherwise, I think there'll be one more video after this. Thank you again, and I will continue to do some regular videos in the future. Thanks again.